Can you see this?
Yes, sir.
Yes, sir. Good. I always want to hear from you so that I know I'm not talking in a vacuum. Okay. So, in the last class, we were essentially looking at particle-particle interactions. And we talked about friction. We did a little bit about, how particles will collide. So in friction, we looked at coefficient of friction. Here in collisions, we looked at coefficient of restitution. And then we did a simple example of how long it would take for a particle that is bouncing on a hard surface. How long will it take to come to a rest? And it takes infinite collisions to come to rest, but we saw that. And then, of course, we talked about how we can model deformation of a particle using Hertz, the Hertz model. Today, I just want to tell you about a few more types of particle-particle interactions. And these are somewhat more specialized. These things are what we will mainly focus on, but there's also a possibility that there may be forces which make the particles stick together. And so what are those forces? Those are known as cohesive forces. And one of them is, of course, this van der Waals force. And this, is given by, this is essentially due to surface forces. And the force of attraction, it's an attractive force. And the force of attraction is just proportional to the radii square, product of the radii divided by the sum of the radii. And then it's inversely proportional to the distance between the surfaces, a squared. And a is called the Hamaker constant. And you can see that it's an extremely small value. So this force, the van der Waals force, becomes very important only when a becomes very, very small. So if a is small, only then this ratio will become order 1, and then the van der Waals forces become important. So this is only when particles come extremely close. And of course, these kinds of forces are very important. Say for and this is one application that now is becoming important. That let's say if you have large particles and you want to put a coating of other particles on them, particles that are much smaller, let's say nanoparticles, then for those particles to stick on the surface, then they stick by the van der Waals force. So since these these particles are so tiny, then the van der Waals force is large compared to the mass of the particle, and hence they can just stick on the surface. So this is one type of cohesive force. But if you're looking at larger particles, then generally the van der Waals force can be neglected. Another force is electrostatic, and this is a repulsive force if you're just looking at one type of particle. Now, these things become quite important in particulate flows because when particles rub against each other, their surfaces may get a charge that collects. So this is known as tribocharging. That is when you build up surface charge on any any surface by just rubbing two surfaces together. Usually, this becomes most common when two dissimilar surfaces are rubbed against each other, and the way it happens is that the electrons from one surface get transferred onto the other surface. Hence, one gets a positive charge and one gets a negative charge. And If there's like particles, this of course this effect is much less. But if you have like charges, then the particles will repulse each other, and this affects the flow. Very often when we are doing experiments, we'll put an earthing on the system so that any charge that is built up is drained away. Because when the charges build up, then the particles start repelling each other, and then they have very odd flow behavior. And the third one, which is also very, very common, is the cohesion due to liquid bridges. So, if your material is slightly moist, it's hygroscopic and all this, then you can actually have tiny droplets of water which act like a bridge between the particles. And then if the particles want to separate, there is a force that acts on them. And this force is due to surface tension, and then also there is a force because of the pressure difference. So there's a surface tension force. That means that the surface is exerting a force because of this contact. It's pulling, the surface wants to shrink, so it's pulling the two particles together. But also because of this curvature, the pressure over here is lower than the pressure outside, and hence there is a tendency for the two particles to come together because the pressure inside is lower. And so this gives us the total force, and this can be quite a large force. In this equation, gamma is the surface tension, r is the radius of the particle, beta is the contact angle, here it's shown, the contact angle, and h star is 2 times h star is known as the curvature, and that depends on the shape of this interface. So there are two types of curvature, that's why there are two radii of curvature given by this and this. So this gives us the total force, and so you can calculate this. Okay. So with that, essentially, it completes what I wanted to tell you about the particle-particle interactions. Now, let me do a few simple examples. Okay, now can you see this?
Yes, sir. Yes.
Good, good. So for the first example I want to do is related to friction. And again, you would have done this type of problem many times in your school days. But just to revise, so let's say we have a block that is on an inclined plane. So this is a plane, and we have a block of some material. Okay, that is on this plane, and this has a mass m. And let's suppose this thing makes an angle theta with the horizontal. And there is a force of gravity which is acting in the downward direction. And let's suppose that there is a frictional force that is acting on this surface, where we are given that the coefficient of sliding friction is, let's say, given to us, and let's say it is 0.36, and the coefficient of static friction, mu, is given to be 0.47. So, what I want to know is what will be the acceleration of this block, at a given angle, at any given angle. So can someone tell me what will happen if, as we go on increasing the angle theta?
Sir, Kunal here. Sir, at a particular angle theta, the block will start moving, overcoming the static friction.
Correct.
And that acceleration magnitude will be g cos theta, I think.
Okay, good. So it's like that, as you go on increasing the angle, there'll be no motion until you reach a particular angle, and at that angle the block will start sliding. But as soon as it starts sliding, the frictional force will come down, and so it will not slide at a constant velocity, but it will accelerate because the frictional force is going to be less than the gravitational force. So, we know that for static friction, that is when the block is not moving, we have the frictional force which is opposing the force of gravity. That is just going to be equal to mu times the normal force. So if you look at this, the normal force is simply equal to mg into cos theta. So the frictional force is going to be actually less than so it will be actually less than or equal to mu times n. And so when it is equal to, that is when it's just about to start sliding, the weight in the direction of the motion, at that point, F will be equal to mg sine theta. That is, the friction force will be exactly equal to that is when you have the equality time sign. So this essentially gives us that mg sine theta is equal to mu into mg cos theta just at the point of sliding. So maybe I'll call that angle theta star. So this is the angle just at the point of sliding. Okay, so these two are not equal otherwise. F will always be larger than this, but only, I mean, F will always be less than this. At that point, it will be equal. And from here we see that this and this cancel out. And so you see that mu is just equal to tan of theta star. So this is one thing that you would have learnt in school, that the coefficient of friction is simply the tangent of the angle at which the block just starts sliding. Now, as soon as it starts sliding, the friction goes down and it becomes mu d. So in that case, your acceleration just becomes g sine of theta star, that is the acceleration due to gravity, minus the acceleration minus the resisting acceleration, or the acceleration due to the frictional force. Now in that case, it just simply becomes, instead of mu, it is just mu d into cos of theta star. So if I want to write this down, this can easily be written as g cos of theta star is equal to just tan of theta star minus mu d, which is equal to g cos theta star into mu minus mu d. So the acceleration is just proportional to the difference in the coefficients of restitution. So this is one simple problem, but it just illustrates what you would get if you had a block on this surface and then it starts. And in this way, we can easily find out also, or estimate, what is the coefficient of friction. So you keep on increasing the angle until it just starts sliding. And then once it starts sliding, if you just measure how the velocity changes with time, you will get the acceleration, and from the acceleration you can get mu d. Okay, so that is one example. A second example is, and I just told you about it, but I didn't solve this in the last class. Time for collision using the Hertz model. Okay. So in the Hertz model, what it says is that, let's say if we have two particles, okay. So you can see this second particle also. So let's say we have these two particles and they're colliding. So what happens is that this particle is going to move, and then when it touches, the particles will start deforming, and then it will keep on deforming until the force becomes large enough. So as it deforms, the velocity reduces and then it goes to the maximum deformation and zero velocity. Now there's an elastic force pushing the particles apart, and so then they go out again. So this is the whole collision. There is an overlap and then it goes away. So there's no force when they are not touching, but when they overlap, there is a force that is there. So we want to calculate how long it takes for such a collision to take place. So if you remember, there is the model, the Hertz model. It depends on the extent of overlap. So, we follow the centers of the particles. So let's say this position is the center of this position particle is x1 and the position of this particle is x2. So we are talking about the centers. So this is x1 and this is, I'm sorry, this is x1, that is x2. And so the distance between the particles I'll call that as delta x is just equal to the absolute value of x1 minus x2. So these are vectors. And when you take the absolute value, this is the length of that vector. So this is a scalar quantity. So here, this is the distance between the particles. And then we had defined this alpha. If you remember in the last class, we had defined a quantity called alpha, which is so this distance, the total overlap, this distance we had defined as 2 times alpha. So alpha is just equal to d minus delta x, where d is the diameter of the particles. So when delta x is equal to d, the particles are touching. And when alpha is greater than 0, then particles are deformed. That is, that there is some sort of overlap that is happening. And we are mainly concerned with alpha to be greater than or equal to 0. When alpha is less than 0, the particles are not touching and hence there is no force between them. And we saw in the previous class that the potential energy is related to the overlap by a simple formula, and this is called the Hertz formula, where K is a material property times alpha, and this is raised to the power of 5 by 2. So this is essentially what you might call Hertz law. And from this we can easily calculate the force, and we saw that N is just minus del Es by del alpha, and we found that this is just equal to minus 5 by 4 K alpha raised to the power of 3 by 2. So this is the force. So, if alpha is positive, alpha has to be positive, so the force is always pushing the particles apart. And when alpha is 0, there is no force. So now what we want to calculate is that we imagine two particles approaching each other with an equal velocity but opposite. So they're approaching each other with a velocity v, and then they touch, and then they deform, and then as the deformation goes on increasing, as alpha goes on increasing, uh, the force magnitude goes on increasing, and at some point, and as the force increases, the particles decelerate, the velocity goes to 0, but the force still remains until it reaches alpha max, and then it moves out, and then the collision is over. So, you can imagine if you plot alpha versus time during a collision. So alpha starts with 0 at, let's say, time t equal to 0. It reaches a maximum, and then this is the end of the collision. And we want to find out this. What is this time for collision? So let's assume, for simplicity, that there is no dissipation. That means none of the energy is lost during the collision. So if the initial velocity, now we'll consider one particle. If the initial velocity is v, then we can write down an energy balance, and the two energy that we have to consider are the kinetic energy and the potential energy. So the potential energy is given by this, and the kinetic energy depends on the velocity. So initially there is only kinetic energy because alpha is 0. So before the particles start deforming, there's only purely kinetic energy. So the particles are approaching with a velocity v. So if we look at one of the particles, then what we'll see is that at the start we have only half mv squared. So that is the energy that the system starts with. Then at any given alpha, we'll have some other kinetic energy. So that's half m, and I'll just call it as v prime squared, where this v prime will depend on the alpha, plus the potential energy, which is just half k alpha raised to the power of 5. So this is the energy balance. Kinetic energy plus potential energy must remain constant. Initially alpha is 0, so there is no potential energy. Later there is potential energy. Now how do we get this quantity v prime? Well, v prime is related to alpha because we know that as the particles move, so at any given time, as the particles move, alpha will change. So we essentially have that v prime is just equal to minus of d alpha by dt. So rate of change of the overlap is exactly equal to the velocity of the particle. So this is after they touch. Before they touch, we are given that the velocity is v, and that is unchanging, and then it becomes this. So our equation then simplifies to half m into d alpha by dt whole squared plus half k alpha raised to the power of 5 by 2. So in this equation, everything is given to us. The only thing we don't know is alpha as a function of time. So if we solve this equation, then we will get this graph. So first thing, can someone tell me what will be the maximum deformation? Just by looking at this, can you tell me what will be the maximum deformation? We'll call that as alpha max. So what will it be?
Correct. Alpha max d alpha by dt will be 0. V prime
Exactly.
will be 0.
Correct. So what happens is, and that's absolutely the correct answer, that when you reach the maximum value, you can see that the slope of d alpha by dt is 0. So essentially that is velocity at the point where the deformation is maximum is 0. So essentially we can drop out this term, and so now we have just a very simple equation. Let me just simplify this before I write down what is alpha max. I just cut out all the common factors. So here you can see that this is just v squared is equal to d alpha by dt whole square plus k divided by m into alpha raised to the power of 5 by 2. So if you want to find out alpha max, then I can just simplify this by first putting this term equal to 0. So then you'll get alpha max is just m v squared divided by k, and this whole thing raised to the power of 2 by 5. So straight off you will get what is the maximum deformation, and what it says is that the deformation depends on the velocity. So higher the velocity, higher will be the uh, deformation, maximum deformation. But higher the stiffness, K is a measure of how stiff the material is, smaller the deformation. Now we work, as I said, we work with quite stiff materials, like let's say steel or glass or something like this. So the deformation is usually quite small. And this is one nice way of calculating in any system what the deformation will be, given what is your typical velocity, what is the mass, and so forth. Okay, so this is one thing. Now, the other thing is, how do you find out the time? And the easy way to do it is, this is now a very straightforward. If you look at this equation, it is a very simple equation. You can see this d alpha by dt. So if we just integrate with respect to time, we should be able to get the variation of alpha with time and hence the time for collision. So if we simplify this out, then you see that d alpha by dt whole squared is just equal to v squared minus k divided by m into alpha raised to the power of 5. Okay. And so, if you take the square root and then rearrange it, then you can easily see that dt is just equal to d alpha divided by v squared minus k by m alpha raised to the power of 5 by 2 raised to the power of half. So this is what it is. And now if you want to find out what is the time of collision, then I can just do the integral and I'll go from 0 to alpha max and then multiply that by 2. And so that will give me the time for collision. And this is an integral that can be done, and so it just turns out to be equal to 2.94 into m squared by k squared by v raised to the power of 1 by 5. Okay, so this is what is the collision time. Now, we have already seen, I think in the last class you may not have noticed it, but I had shown this formula that this K is actually related to material properties. So it is actually 4 times square root of d by 15 into y divided by 1 minus sigma squared, where d is the diameter, y is Young's modulus, and sigma is the Poisson's ratio. Okay, so these are all things that are available. And so, in our problem, let's consider aluminum particles. Okay, of diameter 1.5 millimeters and um, let's say the you're given certain velocity. I'll have to have from my notes. I have to see anyway. So let's say they have diameter of 1.5 millimeters for aluminium. The Young's modulus is given by 6 into 10 raised to the power of 11 times per centimeter squared, and Poisson's ratio for this material is 0.3, and density rho p is just equal to 3, because we need to get the mass, no? So we need the density. So if we are given the diameter and the density, we can easily calculate the mass. So this is all the units these are all the things in CGS units. And now if we are given the velocity, so supposing velocity is just 5 centimeters per second. So from up to here, taking all this diameter, Young's modulus, Poisson ratio, using these three, we can calculate K, and that is equal to 7 into 10 raised to the power of 10 ergs per centimeter raised to the power of 2.5. See, because of the way that this thing is defined, K has to have these units. And then you can calculate what will be your T collision from this. This I'll leave to you to do. Is something equal to 5 into 10 raised to the power of minus 6 seconds. So, even for a material that is somewhat softer, like aluminium, the collision time is in microseconds. This is extremely small. And, I didn't calculate, but you can calculate what would be alpha max. That would be also be extremely small. If you're looking at harder materials like glass and steel, the time of collision will be even perhaps smaller. Okay. And then, I just showed you some examples of, I give you some formulae for cohesion. And one example of cohesion is something called a sand castle. Have you come across this term sand castle? Has anyone ever made a sand castle?
Yes, sir.
Yes. So has anyone been to the beach?
Yes, sir.
Yes, sir.
Has everyone been to a beach, either a river, bank, or
Yes, sir. Yes, sir.
sand?
Yes, sir. Yes.
Okay, so if you actually look at sand, dry sand, it's impossible to make a sand castle. Would you agree with me? So what do you need to do to make a sand castle? So very often the children, what they will do is they'll take a small plastic bucket, they'll fill it with sand, and then they'll make it ulta on the beach, and then they will get this structure, and then they can put a flag on it. So what is happening? These are all sand particles. But if it's dry, this will never happen. If you take dry sand, it'll just go like this. There's no way that you can make a sand castle with dry sand. So what is the difference? Why is it like this? What is happening? Hmm. Can someone tell me?
Sir, the addition of water is increasing the cohesive forces that can keep the what we can say the castle intact.
Correct. Really, the main reason for the dry sand just flowing out is because it cannot withstand any shear force. It just kind of slumps down. But when you have cohesive forces, then you can actually make, and what we'll see later is that this angle, this is called the angle of repose. So there's a natural angle, it just slumps to that. But if you wet the sand, then what is happening is the sand grains have water in between, and that is holding them together. So the particles cannot just move apart, and then you can actually make a structure using this. And so this is an example of cohesion due to liquid bridges. And it's really the surface tension that's holding the particles together. Okay. So any questions about this so far? Okay, so all simple stuff. Um, Let me next, so if we look at our course outline, I had started with some very brief introduction, what are granular materials? And then the next topic was on particle-particle interactions. So with this, I've essentially completed what happens, how particles interact with each other. And there may be collisions, and there may be deformation, and there may be friction. And we've seen that. And different types of particle-particle forces, we know how to calculate them. So then, what are some of the typical characteristics of granular flows? And so to discuss that, let me just show this presentation. And here, I'll just talk a little bit about the characteristics. I'll define something called the inertial number and then talk about flowability. How easy is it for particles to flow? Now here is a list of things which are typical of granular materials. First of all, in some cases they show liquid-like flow, and in some situations they show solid-like behavior. So for example, one characteristic is that, let's say, if you pour a granular material into a container, it will take the shape of the container, it will exert pressure on the walls, and let's say if you make a orifice in the container, then the material will flow out from the orifice. This is, this is very common. You have seen it, that you put sand in a bottle and it'll take the shape of the bottle, and then if you have a container with a hole in it and then you pour sand, then it will come out like a liquid. So that this is all liquid-like behavior. They can sustain a shear stress, and they may even have cohesive strength. So this previous example, I showed you that. Now, a liquid will never form a pile like I showed you for dry sand. In dry sand, the sand will form a pile with a particular angle, the angle of repose. That means it's sustaining a shear stress. You cannot make a liquid form a pile. So that behavior is solid-like. And also we have seen how it can have cohesive strength. And we'll see a little later that the stresses inside may also be non-isotropic. So all of these are characteristics of solid-like behavior. If you look at very slow flows, the shear stress is proportional to the normal stress rather than the shear rate. And it may be accompanied by dilation or weakening. Now all these terms seem a little strange, but we have seen this, that because in the very slow flow regime, since the flow is purely frictional, then as per the friction laws, the frictional force depends only on the normal stress and not on the relative velocity. So we can understand why this happens. And then, of course, when the particles are flowing, I briefly mentioned this also, that they tend to be pushed apart. So there is a dilation that can happen. So this is certainly not like a typical liquid. It's an unusual liquid, so it's not liquid-like. But if you look at rapid flows, the material exhibits non-Newtonian behavior, including normal stress differences. And this is liquid-like, though it's not a Newtonian liquid, but the behavior is liquid-like. But mixtures of flowing granular materials spontaneously segregate due to size and density differences. So, you take a mixture and then it just separates out. So, if you take two different densities, then the heavier particles go to the bottom of the layer, flowing layer, and light particles go to the top. And so this demix or segregate spontaneously. And this is also not what we see when, let's say, if alcohol and water are flowing, you never see them separate out so easily. So it's not like a typical liquid. So you have to take into account things like segregation, non-Newtonian behavior, friction-dominated behavior, and so forth. So these are some very typical characteristics of granular flows. The second thing that I would like to tell you about is that if we want to write down the equations for the flow of granular materials, then one way is, of course, you write the equation for the motion of every particle, which is what I've shown here, that every particle is moving and then you write down the equations for that and so forth. But that's theoretically, it's not a feasible thing to do because there may be millions of particles, and then why do you want to know everything in so much detail? So very often we will replace all these particles moving by a continuum. So if we want to know what is the velocity at this point, then we'll simply take the average velocity of all the particles. So Ci is the velocity of the particles inside this. And if we take this average, which is denoted by these brackets, that is just the sum of all the velocities divided by the number of the particles. That's a number average of the velocity. Then we get the velocity vector v, which is the velocity at this point. So in this way, at every point we can define the velocity, the stress, the density, everything can be defined if we take this kind of approach, that we'll take a volume that is large enough so that this average is sensible, but small enough that it is small compared to your system size. And then we can define an average velocity at every point. And then we can write down the equations just like in fluid mechanics. So we know velocity at a point. So how does this velocity vary with distance, with time, with space, and so forth? So this is the objective that we have, that we have this type of complex behavior. And can we write down simple equations like the fluid mechanics equations to describe this type of flow? Now, as they are moving, things that we have to take into account are, of course, these particle forces, and we have seen those. So you'll have contact forces, there may be collisions, and we have to also, if we are talking about momentum transfer, we have to also take into account translation. That is, as the particles move, they carry some momentum with them, and that also results in stress transfer. So these are the three types of stress transfer that occur: two particles pressing against each other, or colliding with each other, or moving from one region to the other. And all of these result in stress transfer. So we have to take these into account in our theory. When you have slow flows or no flow, then this is the one that's most important. And when we have rapid flows, then these become very important. The collisions, we don't think of them as contact forces, we think in terms of collisions and translation. And so, the theories for slow flows and the theories for rapid flows are somewhat different. And so how do we decide some flow is slow or some flow is rapid? And this can be written in terms of an inertial number. It's a dimensionless number. Now let's imagine that you have two layers of particles. One is moving at a slightly higher speed than the other one, so that we have a velocity gradient given by gamma dot. So gamma dot is, let's say if this direction is x, then that is dvx by dy. So this is gamma dot, called the shear rate. And let's suppose, because of many layers of particles above this, that there is a pressure that is acting on this layer of particles. and that pressure is, let's say, P. So you have these particles being sheared, there's a pressure that is acting, and then of course you have particle properties that the particle has a diameter d and a density rho p. Now we can define two timescales for this particular system. One is the macroscopic timescale, that is the timescale associated with the shearing motion, and that is just 1 divided by gamma dot. Gamma dot has units of 1 by second, so when you take the reciprocal, this has units of time. So this is for the macroscopic flow. Then you can think of microscopic flows that are happening. Because this pressure is acting on all the particles, if a small gap opens up, then because of this pressure, the particle is pushed into that opening. So the pressure will also generate some local small scale flows. And there is another time scale that is associated with those kinds of motions, and that we call as a microscopic time scale. That's because of these really tiny motions that are happening because the particle is trying to fit into some gap here and there. And so we can, based on this pressure, we can estimate that time scale. Now you'll remember that pressure has units of rho times v squared. These are the units of pressure. So if we do rho p by pressure, then this rho p divided by pressure has units of 1 by v squared. That's the units of this. Then you take the square root of that. This has units of just 1 by v. And then if you multiply that by the diameter, then obviously you will get, since velocity is length by time, so this is time by length, multiply by diameter, this will also give you a time scale. So you have two time scales, and then you can take the ratio of the microscopic time scale to the macroscopic time scale. Since both of these have units of time, when you take the ratio, this quantity is dimensionless, and you can think of this inertial number as some kind of a dimensionless shear rate. But it's a very useful quantity, because what happens is if inertial number is very small, that means that the pressure is very large, it's pushing everything together, and so you get a very dense and slow flow. All the particles will be touching each other and rubbing against. So generally what has been found is if the inertial number is less than 0.1, then you'll be in this slow flow regime. However, as you go on increasing the shear rate for a fixed pressure, the particles collide with each other and then they move apart. So the layers move apart, and then they are not all touching each other, they're just colliding with each other once in a while. And so then you go into the rapid flow regime. So there are these two extremes you can think of, slow flow and rapid flow. And if you calculate the inertial number, then you will get an idea of which regime is you are in. Okay. And then this final thing I will talk about next time, which is this idea of flowability. That is, how easily do things flow? And I already talked about the angle of repose, but I'll tell you about other things in the next class. Now, before you go, I wanted to just discuss one thing, and you can tell me how you feel about it. So one, we are going to have homework assignments, a few of them, and we'll have a project. So what Niladri and I, after discussion, what we have decided is that both homework assignment and project should be done on a group-wise way. That is, I want you to form groups of no more than 3 people in each group, and the same group will submit homework assignments and submit the project. Now the whole idea is that I want you to understand these things, and I want you to try out all these, whatever problems I give you on your own. But if you're working together in a group, you can discuss, and things will be a little faster and the load will be a little less. So this is the idea, that you can work together as groups, but at the same time, I don't want intergroup consultation. So I want each group to be responsible for their work, but not consult with other groups. And we'll give the same grade for each group. So as far as homework assignments and projects are concerned, you will give group grades. Okay, so is this okay with you? Anybody have any? So why don't you all start talking to your colleagues and try and figure out who you would like to work with and form the groups. Okay, Niladri has already prepared the rules for this whole thing, so, and some link for putting the groups in. So we'll put that up on Moodle, and you can consult that. But you can already start talking to people and making the groups. Okay.
Yes.
Sir, we have to make our groups ourselves, or Niladri sir, or you will.
I'll give you the option to make it yourself. But if there are a lot of people who are not able to, then I'll make the group. Whatever. You tell me what is your preference.
It will be better if we made the groups.
Huh?
We will
If we
make
make the
ourselves.
groups.
Sorry? Did you say you want to make the groups?
Yes, sir.
Okay. So we'll stick with that, and if anybody has trouble, then I'll help them out. Okay. Is anybody looking at the notes and so forth on Moodle? Are you having any problems with that?
No, sir. No, sir.
No, it's all available now. Okay, good. Okay, see you tomorrow. You can wake up a little later tomorrow.
Okay, sir.